Hello and welcome to the first video of the M2 chapter, Centers of Mass. On the screen is a starter question from M1 to review moments. This is an exam question. If you want to try this before I go through it, pause the video now. A plank of AB of length 6 meters and mass 4 kilograms rests in equilibrium, horizontally on two supports, C and D, where AC is 2 and DB is 1 meter. A brick of mass 2 kilograms rests on the plank at A, and a brick of 3 kilograms rests on the plank at B, all shown in figure 2 here. The plank is modelled as a uniform rod, and all bricks are modelled as particles. Now, a quick review on these words here. If the bricks are modelled as particles, then we're not worried about their size, although it kind of looks like they've got a size here on the diagram. They are assumed to be acting right on the very end of the plank. Also, the plank being modelled as a uniform rod is very important. That tells us that the centre of mass is at the centre of the plank, which is 3 meters from B and 3 meters from A. So I'm going to put that on my diagram now so that I don't forget about that later. Here we've got the centre of mass, and it's 4 kilograms acting downwards, so the weight there is 4 times G. Here, of course, we've got 2G, here 3G, these are all the forces acting downwards. Then we've got the reaction force at C, holding the plank up, and the reaction force at D. Now, we don't know what these are, so let me call this reaction C and reaction D. A little more information I'm going to put on the diagram, even though it's pretty obvious. This distance here is obviously 1 meter. And this distance here must be 2 meters. Okay, I think I'm ready to attack this question. Find the magnitude of the reaction exerted on the plank by the support at C and by the support at D. Okay, so we're just going to find these two values here. I would say there are two standard ways to do this. The first is to take moments about 2 points. For example, you could take moments about point A, moments about point B. That will give you two equations with these two as two unknowns, put them together as simultaneous equations, solve them both, get both answers. The alternative is what I'm going to do. I'm going to take moments about the point C or D. Probably I'll start with moments about D, so I can answer this one first. And the reason I'm going to do that is because if I take moments about this point, the force going through this point obviously has a distance of 0 from here. So when that is included in any of your moments equations, it simply disappears because you have RD times 0. That means I'll have one equation with one unknown, and I can solve that quite easily. So I'm going to start with that. So what I would usually write here is just quickly write what I'm doing, moments about D, and then I would do this. I don't know if this is something familiar to you or not, but what I mean when I write this is that on the left here I'm going to have the anti-clockwise moments about D, and on the right the clockwise moments about D. And if this is held in equilibrium, which we're told it is, then the anti-clockwise moments and the clockwise moments about any point must be equal. So this is what I mean. I'm going to do anti-clockwise moments equals clockwise moments, and we're taking D as our pivot point. So the forces that are trying to push this anti-clockwise about the point D are this one and this one. And I know the distances of each of those two. So we've got 2 times 4G plus 5 times 2G. 2 times 4G plus 5 times 2G. And if it's held in equilibrium, that has to equal the clockwise moments, the things trying to push this clockwise about this pivot point. And that is RC, the reaction at C, and the weight on this side pulling down this way. They're trying to spin it this way around point D. So we've got 1 times 3G, and here we've got 3 times the unknown RC. 1 times 3G plus 3 times RC. And then of course I can just rearrange this to get RC. Here we've got 8 and 10g, so in total 18g equals 3g plus 3 times the reaction. 15g equals 3 times the reaction force, so RC must equal 5g newtons. The question doesn't ask for an exact answer, particularly, but I will leave it like that. Part 2 then is to find the reaction at support D. Now, having started this process with moments about D, I've got two options now. I could do the same thing with a moment equation about C and get a very similar equation where RD will be the one thing I don't know. But there's actually an easier way. Now that I know the reaction force at C, RD is quite easy because as well as being in equilibrium in terms of its moments, its turning, it's also in equilibrium in terms of it not moving up or down. So if I resolve vertically, the combined weight here, here, and here must equal the combined reaction forces here and here. So part 2 here is actually a little bit easier. We can resolve vertically. So we've got RC plus RD must equal the downward forces, 2g plus 4g plus 3g, and I know RC is 5g, so if I put that in, 5g plus RD must equal 9g, then RD obviously must be 4g, and again I'll leave that as an exact value 4g. I've gone through that quite carefully because this is the foundation of most of this chapter. The chapter review here, centers of mass, it looks like a lot, but don't panic. The first 5 are very similar. When I write COM, that means center of mass or centers of mass. So here in this video, we're going to consider centers of mass of particles on a straight line, using pretty much what we just did there, the idea of moments. In the next video, we'll look at the center of mass of particles arranged on a plane. So we'll just take this and turn it into 2 dimensions. Then we'll look at some standard uniform plane laminars. We'll talk about what this word means in that video. Then we'll take a few of these, put them together, and consider composite laminars. Then we'll do the same thing for frameworks. And again, we'll talk about exactly what I mean by that in that video. So these first 5 all build up from this idea of moments. Then we'll look at laminars in equilibrium. Having found the center of mass, we'll do something with it. Same with frameworks in equilibrium, which is very, very similar between these two. And finally, non-uniform composite laminars and frameworks. So to start us off, just looking at particles on a straight line. So we can use our moments knowledge from M1 to find the center of mass, COM, of particles arranged on a straight line. To do this, we take moments about a fixed point, and we can equate the combined moments of the separate particles with the moment of the center of mass. So if you've got a system here, we've got 1, 2, 3 particles, and we consider them relative to the point O over here. We do that so that we've got relative distances. And of course, these are all going to have a weight acting downwards. And often in the book, they will put a dotted line or a straight line to indicate this axis, if you will. And then we make the assumption that we can represent this with a single point. Let's say, for example, it's here. And instead of those 3 separate masses, we've got a combined mass here, acting at the center of gravity. Alternatively, you can think of it as where you would need to put a support force, like we had in the starter question, in order to maintain an equilibrium. Either way you think of it, it gives you the same equations. And of course, you should be familiar with the center of mass. When I say this, what I mean is the point through which all the mass of the system can be assumed to be acting. Like taking a pen, laying it across your finger and trying to get it to balance. There's a certain point where you can balance it, that's your center of mass point. And all of the other points it won't balance. This is very similar to the idea of what we did in the starter question. So I'm just going to go through an example and then we'll talk about generalizing it to a formula. So we've got a system of 3 particles with masses 2, 5 and 3 kilograms. They're all placed along the x-axis at the points 3, 4 and 6 respectively, with 0 on their y coordinate. We'll come back to the y-coordinate later. Find the centre of mass of the system. So if I put a little grid on here, we're not really worried about the y-coordinate, but I'll put it on. The x-coordinate. And then we have our three masses. So 2 kilograms is at 3. I'll put that here. 2g for the weight. 5 kilograms at 4, so that's just next to it, with a weight of 5 times g. And 3 kilograms, or a weight of 3g, is at 6. So this is 3, 4, 5, 6, 1, 2. There we go, something like this. And the question is, where is the centre of mass? Now I like to think of this in terms of a support. So what I would usually do is I would put an upward force, let's say here. And as we had with the starter question, I know what that has to be because I can resolve vertically. Obviously the combined weight of the system is the weight that I'm considering for the centre of mass. So we've got 5, 6, 7, 8, 9, 10. So this is 10g, the total weight of the system. And where I need to push up in order to maintain equilibrium is my unknown distance. And I usually would call that x bar. And the reason I tend to think of it more as an upwards force keeping equilibrium instead of trying to replace these three with a single force equated is because it means I can use my same system that I did in the starter question. Moments, anti-clockwise moments equals clockwise moments. And in these examples, I will always be taking the moments about 0, 0, the origin. So my anti-clockwise moment is the centre of mass, so that's 10g times the x-coordinate of the centre of mass, which I don't know, and that has to be the same as the combined clockwise moments of the three separate particles. So we've got 2g times 3 plus 5g, and that's at 4, plus 3g, and that is at 6 units away from the origin. So that gives us a total turning moment of 44g on the right hand side and 10g x bar on the left. Divide through by 10g, of course the g's cancel, and we get x bar is equal to 4.4. And that's the x-coordinate of the centre of mass. So we can generalize this now to derive a standard result. If I bring up more or less the same thing, where we've got some particle here with a weight, some particle here with a different weight, some particle here with yet another weight, and of course they've all got distances, so this is at x1, x2, x3, and so on, and there may be many particles. It doesn't matter how many there are, it's always going to be the same process. And then we have our single balancing force, or equating it to a single centre of mass force, depending on how you think of it. And this is always going to be capital M, G, where capital M is just the combined mass of all the particles together. And then this is going to be at the coordinate x bar. And we'll always do the same thing. We're always going to have mg times x bar on the left is equal to the sum of the moments m1g times x1 plus m2g times x2 plus m3g times x3, and so on. And every single time you do this, the g's will always cancel out, which is very nice, so we can get rid of those. What we have here then, if we use the sum notation, where this capital M is the sum of all of those little m's from 1 to however many particles you've got, and then this thing is times by x bar. I'll put that on the left to make it clear it's not inside that summation. That has to equal the sum of each individual moment, mi, xi, from 1 to n. So I hope it's clear what I've done there. I've just taken the individual particles, found their moments for each one, put that on one side, and said that must be equivalent to the moment of the centre of mass. And the moment of the centre of mass is the total mass, all of the little masses added together, times the position of the center of mass, which is often the thing that you don't know. Then for the sake of neatness, instead of writing it like this, just writing it as a summation for however many particles you have. Whatever this number is, whether it's 3 like we've got here, or whether it's 10, 20, doesn't matter. And that is the formula that we get for the x coordinate. However, you could just turn all of this on its side and have it pointing up in the y direction, and there wouldn't really be anything different. So you can write basically the same formula for the y coordinate of the center of mass as well. So whether your question is asking you about an x direction or a y direction, it doesn't matter. It's the same process, same formula, just remember to write y bar and y instead of x bar and x. And then just to finish off this nice and formally, let me make it clear that x bar and y bar, they are the coordinates of G, capital G, the center of mass of the system. Now we're not going to do both of these at the same time in this video, but that's exactly what we're going to do in the next video, so we've pretty much done the notes for this video and the next one together here. What we will do is one final example. The point G is the center of mass of 4 particles of masses 3m, 4m, 2m, 7m, positioned here, 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 and here respectively. Now let me be clear on this word, respectively, just in case you're not familiar with the English. That means the first thing in this list matches the first thing in this list. If you don't know that, you can't do this question, or if you get it muddled up, you'll get the wrong answer. Second thing here is at the second coordinate, third weight, third coordinate, fourth weight, fourth coordinate. Given that the coordinates of G are 0, 2, find the value of A. So here we've got a number of things different. Firstly, we don't have the actual masses. We've been told 3m, 4m. We don't know what m is, and we won't know what m is at any point in the question. That's okay. Don't let that worry you. The m's will just work themselves out. Second thing that's different is that we're working with the y coordinates instead of the x coordinates. But again, that doesn't really change anything. We're using the same general approach. We're using 4 particles instead of 3. Not a problem. We can use as many as we need. And the final difference is that we are told the position of the center of mass G is 0, 2, and we're actually trying to work backwards to find the value of A, which is the position of the 3m particle. So although this is one topic where I wouldn't actually draw the diagrams very often, I will draw this one just to help you visualize what's going on. So we've got quite a few things here. We've got G 0, 2, put that in purple about here. We've also got the 7m mass here as well. We've got something at 3, what's that? That's the 4m mass. Minus 2, that's the 2m mass. And then finally, the thing that we don't know, the 3m mass. I'm not sure where to put that, because anywhere I put it, now that I put a scale on, makes it look like I know where it is. Let me just put it up here somewhere. 3m. Another difference here is that I can't really put arrows on here to show what's going on, because really what's happening is that they are kind of going down into the screen. And then the G, if you think of it as a balancing force, is coming out of the screen. I guess I could put left and right arrows, but I won't do that. Let's just get into the equation. So on the one side we've got G, which is all of the individual masses added together, times by its y coordinate, which is 2, and that has to equal the individuals, so 3m times its y coordinate, which we don't know, that's A, plus 4m times 3, plus 2m times minus 2, plus 7m times 2. So we've got 2 unknowns here, m and a, but the m's are everywhere, so they are going to cancel out very nicely. This gives me a 32m on the left, a 3ma, and 22m here. Now all the m's cancel. I take the 22 on the left, that gives me 10 is equal to 3a, so a is equal to 10 over 3. So now I could go back to my diagram if I wanted, and I know that this is nowhere near right. It should be around about here. So this was the sum of the individual masses from particle 1 to particle 4 times y bar, the y coordinate of the centre of mass, which we knew in this case, had to equal the sum from 1 to 4 of the individual moments mi, yi. And in this case it was one of those that we didn't know here. I hope that's enough for you now to have a go at the questions in exercise 3a, and maybe I'll see you for particles on a plane in video 2.